All right, so this is powers of monomials and geometric application. So for step one, the very first thing we're going to do is raise the coefficient to the outer exponent. So you see the example we have above of 4x to the third raised to the second power. So we're going to use the power rule to simplify the exponents, but we raise the coefficient to the outer exponent. So our rule for this is anytime you have a variable with an exponent and it is raised to an outer exponent, we are going to multiply these. Okay, so for our example up top, that 4 right there, we're going to raise that to the outer exponent. So 4 to the second power is 16. And then for our exponent on the inside, we will multiply that with our exponent on the outside. So that will be x to the sixth. All right, so for number one, using the power rule to simplify these monomials, that will just be x to the 10th power. All we do is use the power rule and we multiply those exponents. For number three, notice that the negative 4 is on the outside, so we are not raising that to the power of 3. However, the m to the first power and the n to the fourth we are. So m to the first power multiplied by 3 will give us m to the third, and that will be n to the 12th. For, let's see here, number 5, we'll just keep going down this way. That is a negative 3 being raised to the third power. So again, anytime we raise something to a power, remember that it's kind of like multiplying it out by that many times. So negative 3 raised to the third power will continue to be a negative, and it will be a negative 27. And then we will have x to the 6th power when we multiply the 2 times the 3. So our coefficients in front we will raise to the power, but our exponents we will multiply by that power. So negative 2a to the 4th, b to the 6th raised to the second power. That will be negative 2 raised to the second power will be positive 4, a to the 8th, and b to the 12th. For number 9, we are raising just x cubed, y cubed to the third power. So we're going to multiply those, x to the 9th, y to the 9th. And then we multiply these two monomials together. So when we are multiplying, not raising to a power, we're going to add these exponents. So that will be x to the 10th and y to the 11th. And that will be our final answer. Continuing on to number 11, we have an exponent for both of these. So we're going to raise this to the second power and raise this to the second power. And then from there, we're going to multiply these like before using our product rule that we learned yesterday. So we multiply the coefficients and add the exponents. And that is our final answer there. For number 13, we are going to raise all these to a power. So 2a squared to the third power, 2 to the third power would be 8. So that's 8a to the 6th because we're multiplying. Plus, now we are multiplying these. We're not raising to a power, we're just multiplying. So that will be 3a to the 6th. And now this is adding and subtracting. So this is a great problem reviewing 3 different types of exponent rules. We did the power rule, we did multiplication, and now we are combining like terms. We know to add monomials, they must be the same variable and the same exponent, which they are here. And that will give me 11a to the 6th. I'll do a couple of these over here. I'll do 12 and 14. For number 12, you see this exponent right here. So we need to raise 6 to the third power, which will be 216. Then a to the 6th power, then b to the third power. And the same thing here. If you have 1/3 being raised to the second power, you know how to do this. Don't freak out. 1/3 raised to the second power is just 1/3 multiplied by itself. So we multiply fractions straight across, and that will be 1/9. And then every single one of these exponents is a 1. So when you multiply that by 2, we'll have a squared, b squared, and c squared. Now we're multiplying, right? So when we multiply the coefficients, and then we add the exponents. So 216 times 1/9 is the same as just dividing by 9. That will be 24. A to the 8th power, b to the 5th power, and c to the 2nd power. And lastly, number 14. you have 3x cubed y raised to the fourth power. Feel free to pause this video whenever you need. So 3 to the fourth power will be 81. And then we will multiply our exponents. All right, we do have a power here, so we can't just multiply yet. We need to do 7 to the second, which will be 49. X to the 10th, y squared, times x squared, y squared. Now, this is subtraction right here, and this is multiplication. So we're going to do the multiplication first, and then we will subtract. So 81 x squared y to the 4th stays the same. 49 x, we will add the 10 and the 2, make it 12, and add the 2 and the 2 and make it 4. So now we know when we're combining like terms, they have to have the same variables and the same exponents. Here they do, so we just do 81 minus 49, which will give me 32, and we keep the exponents and the variables the same. So that is your final answer there. Now, when it comes to geometric applications, we can use these same rules and apply them to find these different perimeters and areas. So, to find the perimeter for this, we would need to add up all the sides, not just those two. They only gave us 2. So to find the perimeter, we'd add up 12x, 12x, and 5x squared and 5x squared. Now, we can't combine the 12x with the 5x squared because the exponents for those x's are different. So we're just going to have 24x plus 10x squared. And that will be it for your perimeter. For the area, we will multiply the length times the width. So we can combine them now because we're multiplying. 12 times 5 will give me 60, and x squared times x will be x to the 3rd power because we are adding those exponents. So finding the perimeter here for number 2, we're just adding up all the sides. 10a squared b plus 3ab plus 4a squared b. So you notice that these are the same terms, they are like terms, and the one in the middle is not. So that 3ab is just going to stay there. We can't do anything with it. And then we combine like terms with the other ones, and that is 14a squared b. So there's our perimeter. For the area, anytime you do the area of a triangle, it is 1/2 times the base times the height. So here's your height, here's your base. This 10a squared b is the hypotenuse, which we will not be using here. So we will have 1/2 3ab times 4a squared b. So if we multiply 3 times 4, that will give me 12, and then divide that by 2, that gives me 6. That will be a to the 3rd power and b to the 2nd power when you're combining all of these. So I'll do 4 and 5 with you, and I'll set up the area for number 3. So again, that's a triangle, and the area of this one. The perimeter should be, if it's an equilateral triangle, the perimeter should be 5m to the 3rd into the 4th for all 3 of them, if I'm not mistaken. Yes, it is. So you would do that and add it 3 times for the perimeter. But I'm more concerned with the area, and honestly more concerned with not drawing this video out too long. So 1/2 times the base times the height is how we would set that one up. 5 times 4 will give you 20, times 1/2 will give you 10. That'll be m to the 4th and n to the 9th. All right, so for 4 and 5, they're just asking for the area. So the area of a trapezoid is 1/2 times the height times the bases added together. So base 1 and base 2. We'll call this base 1, we'll call this base 2, and there is our height. So we have 1/2 times our height times the bases being added together. So when we add those together first, that will give us 11 x squared y, because they have the same variable and the same coefficient, and the same exponent, so we can add them. And then we will multiply out. So the 1/2 and 2 cancel each other out, so we will have 11 x to the 3rd y squared when we are multiplying. Lastly, area of a circle. Hopefully you guys know this. It's pi r squared. So whatever that radius is, we will square it. 3xy cubed squared. So if we're raising that to the second power, we need to raise the 3 to the second power, which will be 9. X to the first times 2 will be x squared. Y to the third times 2 will give you y to the sixth. And then tack on the pi at the very end. And that is geometric applications and your